today's session, which is about data acquisition. So let's see. Yeah, there. Data acquisition. That's today's topic. And basically, what I'm going to do, I'm going to go through the slides, but actually, I'm using whiteboard. So, okay, let's put that one on different perspective, and that now it should actually start working. Good. So data acquisition, what is this all about? So what we are talking about is right there on my slide, but a system where we have this sensor that just gives a primary signal, that actually has the transfer function to transfer the physical property into signal. So this is just electrical signal. Okay, after that you need to do something for it. That's basically what you need to do is analog processing, which is signal conditioning. Signal conditioning. So usually you need to amplify it. Sometimes actually the sensors, for example capacitive sensors, you have to somehow measure the capacitance. That would be also part of signal conditioning. So to make the basically the signal match the signal with the digitizer. Okay, and digitizer is usually this analog to digital converter. Okay, and after that you need to do usually some post-processing. And actually that's digital signal processing, what you would do in DSP. Okay, that's the TX00CH31, I think. That's the course code. Oh, CQ. CQ. CQ31 is the course for the digital signal processing course. Okay, maybe we'll have it on next fall. I don't know yet. Anyhow, after that, this signal can be then transferred forward. So we can call this one data. Okay. At some point, in any case, we are going to digital world, we need to do the also some sort of sampling. Okay. Sampling can be done either on the time space or on A to D conversion or on the digital domain. So I would just mark that sampling is actually somewhere there. Even on the post-processing there could be some sampling. Okay. So, another title, and this is about the signal processing, or the signal conditioning, what it looks like. Back to the desktop view. Okay, so for example, how a voice recorder looks like for the signal conditioning. So signal comes first, it's very tiny, you need to do some amplification. Okay, then the next block would be low pass filtering to get rid of some of the noise, or actually also to avoid aliasing. Then there's a sample hold and then A to D converter. And what happens on the signal? Okay, signal is first small and quite noisy. If you take a look at after the amplification is still noisy, you have just amplified it. and then the low pass filter, you get rid of the high spectrum noise, and after that you hold it, take a sample and hold it, so that the A to D converter actually can do the conversion on quantized levels. Okay, so that's what happens to the signal on the signal conditioning. Okay, taking a look at the kind of mathematical way this, or in theory, so the analog signals are actually continuous time and continuous value signals, meaning that it can actually have any value at any time. So basically it looks something like that. Sampled signal. Okay, sampled signal is basically, by the value it's the same as the original. In this case it would be analog, meaning any value but discrete time. Okay, now we have just the samples at certain times, which is nice. Then we can start writing a table. We can have an index table and saving those values. And this is the most common way of doing the sampling. You have a constant sample time, meaning constant sampling frequency. You can do also sampling as you please, but then you cannot basically do any say any sense out of the signal other than, okay, the value was that. It is basically about the same as you will watch the outside. Okay, it's snowing. Well, it's that is the information you wanted at that time, fine, but you cannot actually post-process that information. Okay, so for very good reasons you have to keep the sampling rate constant. All right. This digital signal, actually it is tabled signal, values on a table, and well, it means that it's also, in addition to discrete time signal, it's also quantized in value. So basically you have the nearest nearest integer value to the signal, even for the floating point. There's even there the quantization on the floating point values. Okay, and there's a cat. Okay, going back. So the first step, amplification. In addition to amplification, you sometimes also need to do some biasing of the signal. Most of the modern systems actually have unipolar power, meaning that you can only handle signals that are between 0 and some the power supply voltage, 5 or 3.3 volts or something like that, whatever your battery gives. And for example, those old-fashioned dynamic microphones, which are basically the best microphones ever. Yeah, certainly. These kind of things are only for voice and that kind of things, but still the best microphones are dynamic, since actually it's very linear. It has a wide range of the frequencies it can handle, and it's just the best. Okay, but it by default it gives a bipolar output signal around plus minus 100 millivolts range. Okay, but for example, PSOC microcontroller may have a 5-volt power supply as it has if you power it from the programmer pod. Okay. And then of course the A to D converter there, it has its own reference. You can pick the reference voltage. What is the maximum voltage for that one? So it means that you need to do some amplification and also level shifting for that sort of signals. Okay, so just to keep in mind, and well, this is not a big brainer how to do the amplification of bias. You try to fit. Well, you start from a small signal like that, and you try to fit it in between the 0 and the reference voltage of the A to D conversion. Okay. Then a couple of words about the sample signal. Constant rate, meaning sampling rate, I mark it there with the capital Fs, or sampling interval, which basically is also the sample time. And then you may have already heard about the Shannon's theorem. So if you have a periodic signal, how many samples you need for each period for at least in order to detect that frequency is we basically have to have at least 2 samples for each period, meaning that the highest frequency of what you can detect with the sampler, or well, reliably detect with the sampling rate Fs is half of that Fs. Okay. And if we have too long sampling interval, meaning too slow sampling rate, this will lead into aliasing, and there's supposed to be a picture out of it. Okay, the blue line there is the analog, and then these red circles there are actually the sample points on those discrete time sampling times. So at a constant sampling rate, as you can see, there are something like almost more than 2 cycles on of that analog signal between 2 sample points. And yeah, that what happens. The sample signal, well, you are still sampling, but this is not the signal you actually think it is. After sampling, you see only that sampled part. You don't know that, okay, it was about 2.5 times faster. Okay, to avoid the aliasing, you need the signal condition that you have in the low pass filter, anti-aliasing low pass filter, where the stop band should start at the sampling rate over 2. Yes, sampling rate over 2. So at that point, when the stop band starts on that low pass filter, basically you should attenuate every single information what you have above that frequency, and you have to attenuate those enough. Well, what is enough? It's enough when it doesn't show up anymore, meaning below the least significant bit level onto A to D. This is how it should be done. Unfortunately, you cannot do it every time like that. Okay. So basically you need to go below the Nyquist frequency. Nyquist frequency was the Fs over 2. And more about the designing these filters. So these are analog filters. If you are you making this signal conditioning now, those are analog filters, and to know more, you need to take a couple of analog electronics courses, and of course my digital signal processing course. That's the best. Okay. Okay. So the digital signal now, a little bit more into it. So it's sampled in time and quantized in value, and there are some of course on this process you will get some error. The sampling usually doesn't give you any big errors there, since even at some jitter on the sampling time doesn't affect that much on the result, but the most the biggest the error source is the quantization, and there's actually the signal to quantization noise ratio, and there's even a formula for that one. So that actually gives you some sort of glue if you want, for example, 100 dB dynamic range. So that means that shows you how many bits you should have at least on your A to D converter. So N would be something like 14, 15, no, 16 bits. Yeah, it gives about 100 dB. Oh, that would be 95. For 100 dB you need actually 17 bits. Yes. Okay, so how to select your A to D converter? Well, based on the what is the required accuracy, or actually this is just the resolution, not accuracy, not precision, but resolution, simply given by the signal to noise ratio. Okay, example. So audio signal, actually human ear can detect roughly from 20 Hertz to 20 kilohertz range. You can still hear probably up to 24. I'm an old guy, I can hear only up to maybe roughly 18 and a half. Okay, the highest tones goes first. And then basically that means that you need to have at least 40,000 samples per second for good quality audio. So that's the minimum. And that actually gives also the sampling rate, where that actually comes from, that 44.1 kilohertz sampling rate. Well, that comes from the physics. And also that 44.1 gives some margin for that preconditioning the low pass filter. So you can have 20 kilohertz the actual the signal range, and then still have a steep filter for the anti-aliasing in that remaining 2 kilohertz. Okay, but anyways, it's not by accident that it's 44.1. Why it's 44.1 instead of 44? I have no idea. I'm not that old to remember. Okay. It might actually have something to do with the same fact that why we have this 9,600 bits per second as some factory standard in somewhere. It's actually a multiple of 300. 300 times 2 to the power something is 9,600. So it might be on the same range. From the era of when the computer screen was green on black. Okay, so for historical reasons, that's the 44.1 kilohertz sampling rate, and basically, the audio signals, they are basically acoustic pressure signals, and sound pressure level range is about from 20 to 100 dB. Okay, so basically the minimum requirement for having 80 dB signal to quantization noise ratio gives 13 bits. Okay, few bits more doesn't hurt, but that's why so-called CD quality is pulse code modulated signal, meaning just tabulated values at that 44.1 and 16-bit resolution because it's 2 bytes. Okay, but everyone knows that you need more, of course. If you are listening audio, you need higher sampling rate and also higher resolution. So the very high fidelity would be 24 bits because it's 1 byte more. Okay, It's not 22 bits because you don't save anything, but 24 bits. Okay. And then higher sampling rate. I think the 151 kilosamples per second. Okay, so historical reasons, CD quality PCM signal, and actually, of course, the sampling rate and that resolution, there is also compromise to fit one full long play album on a CD, the original CD. Okay. That's about the sampling. Why I don't? Oh, this is on the wrong place. Sorry. So this actually is for very small signals. Sometimes you actually need to have. This is actually the first stage on the analog signal conditioning, and that would be the instrumentation amplifier, especially on the industrial environments. For example, paper machine. Anyone being in a paper mill? Okay, huge electric drives, say 100 kilowatt electric drive can be there, and then you are measuring something with very high accuracy on and very small signals. Okay, you have big electric fields and probably also long lines from sensor to the this box. You need to do something for the signal. You have to first have very good insulation, but not just that. You also, since you have this wire, sensor and then wire, or actually wire pair, and then you have this electric field. Okay, you will have some sort of electric noise on both lines and same amount. So basically, in addition to this electric signal, in here what you are measuring is UN plus EN. If you just do the amplification, you amplify also this noise. But anyways, since it's on the both lines, you can actually have this instrumentation amplifier, which takes the difference between these lines and basically subtracts these noise parts and amplifies just the signal. So that's the difference between single-ended, meaning the single-ended would be just grounding the other. Yeah, that will ground, but it also leaves the common signal to another wire, okay, and then difference to this that you have that UN plus EN and then 0 plus EN, and difference with gain, you would output would be just G times UN. Very simple circuit. One single amplifier circuit which does the trick. Okay. So basically it's used to reduce the common mode noise and also provides a virtual ground if you want to also have a shielding to this. So you would connect that one to the virtual ground. Okay, more about this topic also it would be on an analog electronics course on, well, electronics degree program. Okay. Then about the A to D conversion, it's you know, if you just select A to D conversion, you never know what you are getting. It's like having a beer, and then they come to you to say you look a little bit foreign, Lapinkulta. Yeah, but that's Finnish. That's the only reason to drink it, right? Yeah. Yeah. So, but that would never happen in Germany if you go to Germany in a bar and ask a beer, they always ask what kind. Okay, that's also the same question should be here. Analog to digital conversion, what kind? That's the easiest kind. 1 bit A to D converter called, well, that's actually a comparator. So basically it's very simple. You have two signals, A and B. A would be your signal from the sensor, and B would be the reference level. For example, if you have an analog sensor that gives relative humidity as voltage values between 0 and 1 volts. 1 volt would be 100% and 0 would be totally dry, 0% relative humidity. Then you can set up a level. Okay, if the relative humidity rises about 39%, you turn some drying mechanism on. Okay, 39% is actually a relative humidity level when iron starts to collect moisture by itself and starts rusting. Okay. So I have actually on my garage I have forced ventilation when this humidity goes too high. But there's also the dehumidifier, but sometimes it's not enough, especially on this kind of weather, driving a wet car there and just kind of thing. But anyways, so it gives information about is the signal higher or lower than something. Okay. A to D, 1 bit A to D converter. All right. If we had a series of, or actually parallel set of these A to D, 1 bit A to D converter with the reference levels, which are basically n times the digitizing level. So those are basically digitizing levels. So if you have a 8-bit this kind of flash A to D converter, there are 255 comparators inside, and separated. The reference levels are separated, you know, so that you have all the bits there. So basically, after that, you just need a priority encoder which gives 8-bit precision. Within 8 bits, it gives the what was the highest comparator going high. Okay, easy. Yeah, that's also pain for the this silicon engineer to design. So these are precision comparators in one single chip. But this is the way you get up to 40 gigahertz signals. No other A to D conversion method can do it. Very fast. You can make very fast converters, but yeah, they are, of course, they are a little bit pricey because of the complexity of the circuit. The analog part. The digital part is quite simple. It's a priority encoder. Okay. Complex circuit, and those are expensive, but for example radar applications or digital sampling oscilloscopes with say higher than 100 mega samples per second, those are using flash A to D conversion because there are no other things. Okay, on the other end, the well, another thing about the A to D converter, it's very hard to get more than 10 bits out of these. Or well, it can, but then you must have military budget. Okay. So for on the other hand, say most of the real-life signals are quite slow, or actually the need for measuring is kind of slow in most of the cases. like temperature. You do not want to or need to measure temperature, with a high speed. Not in Finland. Twice a day will be just fine. Check cold, and 12 hours after, still cold. Yes. Yeah, right. But then this integrating A to D conversion actually is quite the opposite to the this flash A to D conversion. Basically, this is sluggishly slow, but with high precision, accuracy, and resolution. So fundamentally what this one does, it has an analog integrator. Have you studied the operational amplifiers? You have, and you have you? Okay, but anyways, with the operational amplifiers, one of the basic circuits to do there is a integrator, which simply gets the signal as current signal and uses capacitor to actually have the integral of the input signal as on the this integrator output. Okay. So if we had a device that makes a perfect integral of the signal, time integral of the signal, and then if we had basically an analog multiplexer, so this box here, that's an analog multiplexer, that basically first we select the input signal, start integrating it for a given, or is it given time? Yes, for a given time, constant time. Maybe I should actually make a small picture of it. Wait a minute. Okay. Small picture. So, constant time. So that's fundamentally well, I'll just make it TA. So this is a TA for integration. Well, time TI for integration. So the signal, the system starts integrating the signal, and basically signal varies, but this one goes to some level. It doesn't usually have that much noise on it. It reaches some level, which basically is proportional to integral to 0 to Ti of that signal x dt. So it measures basically this area right here. And after that time, we turn the switch on the other and start actually counting time. So we are measuring the time here, what it takes to down integrate with a constant value, reference value. So this actually is here then that area is proportional to, well not minus Ti reference dt. So it's just an average reference. And basically the time that integrating time is then directly proportional to the value where it started. So this is quite genius way of calculating what is the average of the signal. So integrated average of the signal. And what makes this very accurate is that on the digital era, the time is one of the easiest things that we can measure accurately. And then also the high precision. It also requires that there's something more than just those. Also the accuracy of the components. This integrator, if we had, for example, on the integrator we had this capacitance, constant capacitance. If the capacitance is not constant, what it actually then gives, if you have a little bit lower capacitance, yeah, then you would end up having a little bit higher signal here. But on the other hand, you also have higher integration time. So basically the changes in the capacitance is cancelled out. So it does not affect on the precision of the A to D conversion. Okay, what else? Even the reference voltage, it's not that critical as long as it doesn't change during the sampling. And on the other hand, these reference signals, they can be done with very, very high accuracy. And then I also told you, so basically the biggest inaccuracy here is the time. And those are pretty darn accurate clocks what we have nowadays. Okay, so basically that's how it works, and that's why it gives very high precision the data. So typically the integrating A to Ds, it's hard to find a good integrating A to D with less than 16 bits accuracy. So they start at the 16 bits, where this is the absolute maximum for the flash A to D conversion. And then they go up to, I think highest that I have seen is 40 bits. So in 1 millivolt level, 40 bits is a lot. It's a lot. So it's nanovolt level, right? 2 to the power 40 is, whoa, yeah, it goes to, let's see, 10 bits is actually 10 bits is same as 1000, right? Okay, so 1 over a million. No, yeah. Yep. Yep. Mm-hmm. So you can see all kind of noise there. Of course, it's a good thing. Okay, that was the integrating. So if you need very high precision with lots of bits and you have time to do the conversion, then that's your choice. Most common the type of A to D converters is actually sigma delta. And the popularity actually comes from the audio signal processing. Those give the properties are very nice to make all kind of sound equipment cheap. This is cheap technology. There's different configurations on how sigma delta works, but fundamentally you are integrating a difference between input signal and a D to A conversion of that of the 1-bit serial input. So in principle, this gives a differential value. Was the current signal higher or lower than the previous signal? Okay, that's the fundamental conversion. 1-bit serial conversion. Was it higher or lower than the previous? Good. Okay, with high enough sampling rate, this is enough. It starts following the input signal very closely. Okay, the catch here is that actually that 1-bit serial output is then there's some heavy post-processing. So the accuracy or the resolution is increased by summing this 1-bit serial output, or actually digitally integrating the serial 1-bit output, and then some filtering, of course, there, anti-aliasing filtering. But everything after that is done on digital domain, which means that very little number of analog circuits there, and some fast logic circuits, which means this is the cheapest technology available. Okay. So fundamentally, the 1-bit serial output is a pulse proportion modulated digital signal. So pulse PPM modulation or PP modulation. That's supposed to be in some of the courses of the on networking. Okay. Anyhow, then this is then decimation. The decimation means that the getting more bits of the data by running a integral or sum of it, and that also lowers the sampling rate. So initial sampling rate is very high, but then by decimation you can basically have, say, more resolution when you just have less frequent samples. So making the the final sampling rate lower, you can actually increase the resolution. Okay. So the problem actually, or challenge in here, is the baseline drift. Okay. And that's the challenge of this technology. So if you need high precision, then still the integrating is almost the only answer. But if you need high resolution, this is the cheapest, which means the best. Ask your boss if you don't think so. And these are used especially in audio. I don't see any reason to use anything else on audio. And even some of the video A to D converters are nowadays the sigma delta type. And there actually the nature is quite sometimes nature is like outside, but sometimes it actually works for you. Another thing about sigma delta is that for higher frequencies, or because of the decimation, you are actually start to cut the frequencies. So very high frequencies you cannot detect with this one at all. But on the other hand, the nature works that basically if you have some decibel level at, say, 100 Hertz, then the decibels start going down 6 dB by octave by nature. So if you have any music, you can see basically that there is very little information on the high frequencies. Okay, so that'll be just fine for that kind of applications. Audio, excellent. All right, then something in between. So sigma delta, low precision, high resolution, and the speed can be compromised with the resolution. So resolution is basically inversely proportional to the speed. Okay, this is kind of midway technology, successive approximation. Well, it is successive approximation register type of A to D converter, where you can have relatively high sampling rate and high precision at the same time. So basically, let's see. There is a D to A converter and a digital logic that actually clicks some bits on the D to A. D to A's are quite simple to make with a high precision. That's the. Then there's one comparator, and fundamentally you're starting to guess what is the input signal value based on the Newton's halving formula. You know how to find a 0 point using that Puolitus-sääntö, Newton's method of finding a 0 point. This is exactly the application of that. So first, if you don't know anything about the signal, you first try to find it at the midway. So highest bit up. If the signal was still lower, then you know, okay, next bit would be, you fix that highest bit and then try the next bit. If this actually was bigger than the input signal, then you would just know, okay, this bit is 0. Next you try the next bit. Leave the first bit or the highest bit as it is, and then go and test the same for the second highest bit. Do the same thing, is it lower or higher, move to the next one. So basically, if you do 10 comparisons like that, you have 10 bits. Very high precision and also quite fast, since you can do those comparisons at rates up to say 100 megahertz, which means that you can have in order of 10 megahertz sampling rate for 10-bit A to D. Pretty good. You cannot do the same rates with the same resolution, or well, the same accuracy with these sigma deltas. And then flash converters would be much more complicated, which means more expensive. Okay, so that kind of SAR type of analog to digital converter would be your correct choice. Okay, I already told you how easy it is to make the digital to analog conversion. Yes, it is. For example, PSOC has digital to analog converter by itself. Couple of things. Okay, one, the most of these high precision digital to analog converters actually are somehow basically just a weighted some kind of devices. So there are reference levels which are basically representing the bits, the weights on each bit, and then you have these multipliers and then some summing amplifiers. Ta-da! Done there, been that. Okay, I have kind of there are these voltages. These are usually done with the currents, but it's the same thing. It's inside of the chip and easy to get a lot of precision on a single chip, and also fast, since whenever you switch those data bits there, then basically the summing amplifier, as soon as the summing amplifier has settled, you have the analog output available. Okay. Sometimes you are unlucky and you need to do the pulse width modulation, or well, the D to A conversion yourself. And of course, it's you don't have those on shelf, and you need to do it today, and that kind of thing, that kind of situations. Okay, PWM is a D to A conversion. It is. If you need a voltage output, you just need analog low pass filter, and then it's, well, decent D to A signal right there. Or actually, you sometimes don't need that low pass filter electronically, But for example, in lighting applications, these LED lights, which has a dimming control, they are just, you know, have high enough frequency so that the human eye doesn't see the blinking. Anything above 25 Hertz, it looks constant. Okay, so that's the simplest way. PWM, you just need to take care of the high enough rate, the base period, or base frequency for the PWM. Or there's also, of course, earlier I told you about the pulse proportion modulation. It's relative. It's almost the same, but okay, a bit different. So this pulse width modulation, you have a constant period, and you just change the width of the duty cycle. Plus pulse proportion, you can also change the off time. It's basically you change off time and on time. Or electric motors, yeah, PWM signal is all okay there. The one in particular, the servo control is PWM, plain PWM. Okay, and then there's the sound application, yada yada. But PWM has, if you are basically running very high loads, and then there are some EMC regulations, of course. For example, those paper machines. It's not that straightforward. Hey, PWM, then it works. You might actually see some high frequency, high current arches forming if you just run those as you wish. Okay, that's all for the signal conditioning for today. So now we have a short break, and then we'll continue on today's exercise. Let's see, what is today's exercise? Data acquisition on PSOC. Yeah, so we'll take a look at what PSOC actually has, what kind of A to D converters there are, also how to do analog routing of the signals, and third one, the sampling, meaning interrupts, timer interrupts. Okay, let's have, say, 15 minutes break so I can have a cup of coffee.